Good afternoon, everyone. Thank you for coming. Hope that you're ready for the weekend. But before, we have a treat here. So we have Friedemann Heinz from University of Freiburg, and he will be here also next week to work with our group. Freddie, as some people know, he did his physics degree in University of Freiburg and graduated in 2010. And then he did his PhD in University of Freiburg with work in Fraunhofer ISE and become one of the world experts in spectral PL measurement. And we really enjoy to read always his papers, and his thesis is quite amazing masterpiece. So we have this opportunity to host you here for 1 week. After that, he will go to ANU to see how they do stuff in Canberra as well. Definitely, you will not have this crowd and cameras for seminar. So Freddie will speak with us about his work on transient PL, and he also promised some work on trapping as well. I hope that will be. So please welcome Freddie here.
So good morning or good afternoon, everybody, to my talk about transient photoluminescence spectroscopy. Photoluminescence spectroscopy is generally a quite powerful technique, simply because it's a direct measure of the electric properties of silicon, like the charge carrier density. And it's by now widespread. There are different approaches, but still all these techniques using photoluminescence are rather young, simply because the emission of silicon as an indirect semiconductor is just notoriously low. So it's hard, like technically, to measure the photoluminescence. Yet there were early investigations, like for example here in the 80s, where Hangleiter measured the transient decay of the charge carrier density using a photomultiplier. This measurement already looks quite nice, but as you can see, quite high injection densities here, 10 to the 17th, were required to obtain a sufficient signal-to-noise ratio. And this is not always easy to interpret. Yet there were new detectors and new approaches, especially here at UNSW, a lot of development by Trubke, who, for example, used simple silicon diodes, which are rather old, but still for measurement it was not easy, or Ingus diodes, which came up lately to measure the injection-dependent charge carrier lifetime. So here on the right you can see that's a very important parameter for silicon, the lifetime as a function of the charge carrier density. And up to then, photoconductance was the only, or the most sensitive technique, or the most widely applied one. And now we have another one using photoluminescence, and you can also see there's differences between those two techniques. That will be interesting later. And here you can see the charge carrier densities, the first measurement I showed before here, 10 to the 17th. Here it's going down to 10 to the 8th, so an increase of sensitivity of 10 orders of magnitude. Later, silicon CCDs were used then to measure spatial resolve, the luminescence emission. For example, here on the right you can see as a multicrystalline silicon wafer, where now luminescence can be collected from a small volume, like for example 100 times 100 micrometer, directly monitored to 1 pixel of a silicon CCD, and within one measurement, 1 second for example, you get the whole spatial resolved information. Later, that was the work while my master thesis and my supervisor introduced Ingus line CCDs to do microphotoluminescence mapping. So using a confocal microscope, doing pointwise excitation and pointwise detection. And this gives us highly resolved photoluminescence maps. So with the drawback that we have to raster scan the sample, which takes a while, we get a very high spatial resolution. But still there were problems in quantification. So here on the right, this the scale, shock rate Hall lifetime. The lifetime, it was very hard to get this scale. By then we did it using intensity comparisons, but that's also always a very not a good approach, because intensities are always prone to variations, experimental variations. There's a large error on an intensity measurement. Now the other techniques before here, they used time domain to measure the lifetime. And so I was thinking, okay, can we do this also for microphotoluminescence? And so I came up again using time correlated single photon counting to be able to measure highly sensitive the charge carrier lifetime. And this was the beginning of the work I'm showing. And then I will go a bit further of my thesis and show what we can do with this highly sensitive method. So in the first part, I will briefly show the experimental advanced. Well, the experiment itself, it's quite simple, but the more cumbersome or the harder part is the interpretation and the evaluation of the data which can be obtained. In the second part, I show two applications, how we can use this experimental setup and interpretation to do microphotoluminescence mapping in a quantitative way, and also to separate surface and bulk recombination. And then in a fourth part, I'll show some new results on trapping. So time-correlated single photon counting is in principle a rather simple technique. It seems like a simple technique. So we have a laser pulse which starts a timing trigger. So the laser pulse is here coming onto a sample, and we measure the emitted photons. So one laser pulse starts the timing trigger. Then later we have a detection of a single photon. Then we correlate these two events. This can be done with a very, very good time resolution, well below a nanosecond. And then we repeat this, another pulse, another detection, and slowly a decay characteristic builds up. This was very long thought to be a very inefficient technique, but actually that's not the case anymore. Electronics got faster, detectors got faster. And then we have several benefits of this technique. On the one hand, we have very low dark count noise. So generally, single photon counting has a lower noise than analog techniques because, for example, thermal events which would differ in the pulse height we detect can just cancelled out by a fraction discriminator. Then this gives us, in the end, a very sensitive technique. So we can resolve maybe 1 photon per minute by integrating very long. This is possible with a low dark noise. Just for comparison, an INGAS diode could usually have like 10 to the 5th count per second dark noise in an analog technique. Well, the high time resolution, because of this very fine resolving correlation. And then a very high dynamic bandwidth. Well, we can simply use very long pulse distances, then we can measure hundreds of seconds, which can be measured, or just very short pulse distances. It's important for the long pulse distances that we don't only count one photon. So in this part, my setup deviates from the classical setup that we count all photons coming after a laser pulse. So let's show some first measurements or a proof of principle. On the left here, you see now the amount of detected photons as a function of decay time. There was a laser pulse in the beginning. This is a standard Stokhalsky sample. And you can here see the rough exponential decay. Now, from this decay, we can, from the detected photons, we can deduce the charge carrier density. And from the charge carrier density, then the injection-dependent lifetime. And this looks something like that. So here we have the lifetime in microseconds as a function of injection level. As a cross-check, I repeated this measurement, but with a higher pulse energy. We see that actually there's a strong deviation or a strong inconsistency between these two measurements, which was in the beginning quite surprising because the experimental setup is quite simple. And how could this happen? And also compared to QSSPC, a well-established large-scale technique, there's a large deviation between the measurements I did and the QSSPC measurement. And now let's look a bit into detail because this is interesting. I found similar deviations also in literature. For example, here microwave PCD, where you can also see this increase in the beginning, where these curves do not correspond to each other. And now looking here that there's a general deviation, I wouldn't even be sure that this consistent areas are the true lifetime. I found the origin in this in a kind of basic thing. So what we do experimentally is measuring the photoluminescence integrally over a certain volume. So the volume is defined by W. So now in the following, I will just leave out the time dependence. Well, everything will be time dependent in the following, but just for notation. So here on the right, again, our sample. Here's the cross-section cut of the sample with the sample depth. And here, assuming illumination from top, then, for example, the detection volume could be something like that, some square centimeter or something. Then what happens after laser pulses, of course, diffusion. But I don't want to talk about diffusion too much because it's kind of obvious that you have to take care of that. The more important thing I found is that the photoluminescence has some kind of dual use. On the one hand, of course, here the photoluminescence is a function of charge carrier density. It's a measure for the charge carrier density. But on the other hand, the photoluminescence emission, which we detect, is also some kind of detection probability. So comparing, for example, this volume here to this volume here, this is also inside our experimental detection volume. However, there's no photoluminescence emitted from this volume here. So this does not contribute to our signal which we measure compared to this volume. So what's the relevant average of the charge carrier density? So usually we would say, okay, the charge carrier density is the average over the detection volume. But this cannot be rather true because the charge carrier density here, the low one, doesn't play a role. Here, if we want, in the end, average charge carrier density, we need to introduce here the emission probability from the sample itself, which just means the average charge carrier density is somehow confined to the volume from which we have photoluminescence emission at all. This is quite complicated, but there are some special cases. For example, special case 1, if we have steady state conditions, if the detection volume is small compared to the generation, if the wafer thickness is small compared to the diffusion length, then this weighting is simply 1. So this is the classical situation in photoluminescence imaging. We have homogeneous illumination, diffusion leads to a homogeneous depth distribution, and so the average of the charge carrier density is quite simple. The other special case would be if the diffusion length is very small compared to the generation profile. If we are in low injection, then the distribution of the charge carrier density is always just given by the injection profile of the laser. This is in silicon usually not the case, simply because of the large diffusion length, but maybe, for example, in direct semiconductors, this would be an approach. But can it be generally treated, this problem? So this is our average charge carrier density we want to talk about. So at first we need to originate from the microscopic charge carrier density. This is given by this equation of continuity. In the transient case, for simplicity, we have no generation, so here recombination, diffusion. What we are interested in is the intensity-weighted equation. And so we apply this average to this equation, and we obtain a macroscopic equation as a function of time. And the average over the volume cancels out the R dependence. And what we find that, of course, we have the diffusion, and here another term which just originates because the time dependence does not commute here with this term, because the luminescence is also time dependent. So we have an additional term here. And compared to the formula to calculate lifetime, we see the difference here. We have here the recombination term. This is simply this one resolved towards tau equals to this, but then the diffusion and this term are missing. But now this cannot be simply solved towards the charge carrier density because this term itself, it depends on charge carrier density. But it can be solved iteratively. I want to show you this. So I did a simulation of the experiment. So on the right you can see a lifetime, which I assumed. Lifetime is a function of injection level. So this is just what I assumed. From this, I calculated on the sample the microscopic distribution of the charge carrier density. And from this charge carrier density, I calculated the photoluminescence in every volume element. From this photoluminescence, I can calculate the experimentally measurable integral charge carrier density if I weight this one with the detection probability. So this one determined experimentally would look like that, for example. And then we get, again, a curve, detected photons as a function of time. If I now calculate here the lifetime like we did before, we again see that the measured charge carrier lifetime deviates from the assumed one. And this kind of resembles the experiment I did. But this can be solved iteratively. So this is our first measurement, or similar measurement. But this one we can take as input to the microscopic equation, calculate the luminescence emission, calculate the diffusion and this gamma term, these two terms which are new now, calculate a new lifetime, and from this new lifetime start from the beginning and iterate this. And we can actually see that after some 28 iterations, we reached the original assumed lifetime. And this is quite promising. So I applied this iteration technique to the experimental data, and we can actually find that now with a new evaluation, we get a consistent data set with this approach, and also a consistency with the QSSPC measurement. So this is a bit complicated, but is a general important. So as we saw before, for photoluminescence imaging, usually this is just automatically taken care of because it's a special case one. But for thick samples, for example, ingots, this is a problem, and Bowden showed that it had to be considered for, and this work by Bowden is a special case of this, what I showed before. Micro FPCD is very important, for example, because here we have focus excitation, we have a lot of diffusion, a change in the luminescence emission, and then low lifetimes, where the depth diffusion is not sufficient to generate a homogeneous depth profile in the sample. And there's also important that luminescence is mainly emitted from the front side, but not from the whole bulk. So here I show some lifetime curves I measured, so we can cover a quite wide range from very low injections simply because the technique is so sensitive, but also high injections here because we can focus to a small spot. Also it's possible to measure just low lifetimes here, some 100 nanoseconds. It's no problem, and the thing is that these measurements were all now conducted on an area of 50 micrometer in diameter, and this makes it quite interesting for microphotoluminescence. So this was the original reason why I did all this. So let's show an example. Here on the right you see a photoluminescence image. The PL intensity will focus here to a small 3 × 3 millimeter area, and it's kind of blurred. They have a lot of lateral diffusion. Compared to a microphotoluminescence map, we can see here a lot more details. But again, up to now it was hard to write here a lifetime instead of the photoluminescence intensity. But what we can do now is look for a homogeneous spot, do there the transient measurement, which takes a bit more area than the usual spot sizes of microphotoluminescence, and then calibrate the whole map. And what we get then here, for example, with logarithmic scale, is a quite nice map of the charge carrier lifetime. To compare it a little bit better with the photoluminescence image, here with in a linear scale, you can see, okay, it kind of resembles, but is it really true what I'm doing? So what I did next is a simulation of this photoluminescence image. So I assumed that this lifetime on the left, measured with microphotoluminescence, is the true lifetime, and then I assume the homogeneous illumination like imaging is using, and then from this calculated the lateral diffusion which would take place in this case. And then we can see actually with lateral diffusion we get quite similar results, and only here in the low lifetime regions, probably due to optical blurring, so scattering of photons in the CCD detector, there are some deviations. But I think that's quite nice. So with the drawback that the right measurement here took probably a second, and this one took an hour, we get just quite more information. For example, we can see that the lifetime in this area here is not some, I don't know, like 50 microseconds, but rather 10 nanoseconds, which is just a lot lower than we would assume from the photoluminescence measurement. So in the next part now, I will go away from this micro applications and rather just use the findings before, where we found that with focus excitation, we have a lot of diffusion. It's complicated. We go now to applications, so we have just extended laser spot sizes, and we do not have to care about this weighting problems. And this leads us to the measurement of the surface recombination. So surface recombination in steady state leads to some kind of effective lifetime. So we have a lower lifetime than the bulk lifetime simply because we cannot distinguish if the charge carrier is recombined at the surface or in the bulk. For the transient case, this could be different. So Luke and Cheng proposed that carriers which are generated near the surface will also recombine fast at the surface if it's recombination active. So they did some simulations, this was in the 80s also, that here you see the depth of the sample, 50 micrometer thickness, and here on the top you can see the excitation profile, so exponential decaying with depth. And after some afterwards, so after the laser pulse or after the excitation pulse, the charge carrier density drops fast at the surface and not so fast in the bulk. And this should be promising. So measuring the transient decay, this should be somehow separable, the surface and the bulk recombination. Yet they didn't have at this time sufficient experimental equipment, because if you look closely, these time scales here, just 10 nanoseconds, and then most of the action already took place. It's hard to resolve it. And there were several approaches in the following decades, using like photoconductance, reflectance, current, just everything you can imagine. But in most of those cases, it was hard to interpret the measured data. On the one hand, often the excitation pulse was too wide or not narrow enough. And also, like reflectance, it's not strictly linear with the charge carrier density. So photoluminescence at low injection is linear to charge carrier density, so I tried this out. I took this simple setup up here, so measuring on a large spot, measuring the decay with 2 different lifetimes, just to see the difference. And here you can see, for example, with infrared excitation, we have a fast initial decay, and then the exponential decay for longer decay times of several microseconds. If we excite surface nearer, we have a stronger initial decay. Well, this I think is quite clear. If we excite with a shorter wavelength, we excite the carriers more surface near, and then more carriers recombine near the surface, of course, as the surface. What can we do with it? To evaluate these curves, I simulated the photoluminescence intensity. And for example, here you can see for a certain pair of surface recombination S and bulk recombination tau, we actually can quite nicely describe this, this decay curve which we measured experimentally. Now, to get an estimate of what values of S and tau could describe this, this sample, I calculated a reduced chi-squared, so the difference between the experimentally measured decay curve and the simulated decay curve for different surface recombination and bulk recombination. And then what we get here, what I plotted here is surface recombination, here is bulk recombination, and then we get a certain area within one standard deviation of the minimum reduced chi-squared, so the minimum of the fit, within which possible pairs of surface recombination and bulk recombination must lie. So we see, for example, here the bulk recombination must be above some 50 or 60 microseconds. And this is quite remarkable. If we think that here the effective lifetime, the asymptotic decay, it's only 3.5 microsecond. So this is a bare sample without surface passivation. We can also look at an area which is 3 times the standard deviation. So how much is this? 98% must lie within this area. Doing the same for the more surface near excitation, we get another area. So here you can see we are more sensitive to the surface now. Well, simply because we have here like more information within the scattering of data, and we can find, okay, the surface recombination must actually be between 5,000 and 10,000 centimeters per second. Yet we can say less about the bulk recombination simply because you can see here the scatter of the data is just much stronger for more surface near excitation, because we lose a lot of signal in the beginning, and this noise here is just given by Poisson statistics. So this is if we have here 100 counts, then we have square root 100, 10 counts error. I tried the same with a passivated sample. Here, aluminum oxide passivated, but we can see that we can get this confidence area where our pairs of surface and bulk recombination must lie, but we cannot distinguish between surface and bulk recombination. So this is actually, so we see that here our technique is limited in sensitivity. We just know that if, for example, the surface recombination is 1 centimeter per second, we can say, okay, the bulk recombination then must be 1 millisecond. Then I did the same for a one-side passivated sample. For this purpose, I measured the decay from one side, from the passivated side. Then we get this decay curve. Then turn the sample around from the unpassivated side, then we get this curve. Okay, this is also quite clear. If we measure from the unpassivated side, we get a lot of surface recombination. This is not the case for measuring from passivated side. Well, now simulating means that we have to simulate the variation of 3 parameters, front and back surface recombination and the bulk recombination. And now plotting this gives some kind of confidence volume. So in this case, we can see that, okay, the non-passivated side must be 10 to the 5th centimeter per second. The passivated side is below 200 centimeters per second, and the bulk recombination is above 50 microseconds. So this is the information we can get from such a measurement. This is working quite well, but now I want to look at something else which I found within these measurements. So these were the curves I showed before, but what happens if we go now here to lower excitations for the Shokhalsky-grown silicon sample? We would expect, like compared to the float zone and the chromium contaminated sample, that for low excitation this is also constant. Well, this is the normal behavior of Shokhalsky Hall limited samples. But actually that's not the case. So what I find is lifetime curves which behave like that. For example, here 2 different samples, here measured with modulated photoluminescence in quasi-steady state, and then with the transient measurements, so with pulse excitation, we first underestimate the lifetime, and then we strongly overestimate the lifetime for low injection conditions. And this resembles quite much like the trapping effect. So we had this curve here before where trapping leads to apparently high lifetimes at low injection for photoconductance. But now this is interesting because trapping shouldn't affect photoluminescence. So let's go a bit into detail with this. So there are different concepts of traps. I want to show here a very simple concept of traps which explains all of the observations we will see in the following. And this is assuming a deep energy level in the band gap, like for other transition metals or something. And then this deep energy level can capture, for example, in p-type silicon, an electron. But instead of recombining, this electron can be emitted back to the conduction band. This is what I want in the following to denote as a trap compared to a recombination active trap, where the electron would recombine. So what we have is an energy level which can capture electrons but is not necessarily recombination active, and if no hole is captured, then the electron is at some point simply thermally emitted back to the conduction band. So what implies this for photoconductance? So for photoconductance, this leads to some kind of photodoping. If we have steady state illumination, slowly all traps will be filled. But if the electrons are captured, the respective holes are still present, and this leads to a higher hole density. So for the measurement of the conductivity of photoconductance, the measured photoconductivity is composed of the excess conductivity, so the conductivity of the generated excess charge carriers, plus the conductivity of the electrons trapped in traps, given by the respective holes. So as soon as the trap density exceeds or gets comparable to the charge carrier density, we get apparently high lifetime, simply because we have an apparently high photoconductance, but it has nothing to do with the recombination lifetime. This is different for a measurement of the photoluminescence, because with photoluminescence we have the product of electrons and holes. For example, for p-type, the holes, we add here the doping density, and then to the doping density we add the amount of trapped electrons, because these trapped electrons lead to excess non-trapped holes, which are still present. But yet, as long as the doping density is larger than the trap density, this shouldn't have any influence, and this is usually the case. In steady state, we do not expect this to happen. But what about the transient case? There it could be different. So the simple case of low injection, this will be the case in the following. we have only the product of free electrons and the doping density. The excess electron density doesn't play a role. And what happens now if we have a change of the photoluminescence intensity? So either we need to have a change of the excess electron density, or we have a change of the doping density. So both could be possible, but in the following I will focus to a change of the electron density. This is the way more simple approach, and as long as there's no reason to doubt this, that this might be the case, and just to make it a bit more simple in the following, I will always talk in a change of the electron density, also because a small change of electron density at low injection can already lead to a high change in the photoluminescence intensity. For the same change in the photoluminescence intensity, we would need a rather large change in the doping density to maintain this relative change. So what we observe now, before I showed the lifetime curve, here now is the decay curve of the photoluminescence, and now if the doping density is constant, this is the decay of the free electron density. And what we can see is in the beginning we have this exponential decay according to recombination lifetime, and this merges into some kind of a tail which leads to this apparently high lifetime. And this could be understood in the concept of electron traps. So imagine we have a laser pulse in the beginning. This would generate electron hole pairs, and then some of these electrons would be captured into traps, and in the meanwhile all the other free electrons decay. If these free electrons have decayed, at some point these might be re-emitted. This might be a slow process because the thermal excitation from this deep energy level, this would be slow. And this can then lead to a generation of electrons due to occupied traps for long decay times, here is 1 millisecond, and then lead to a photoluminescence. Now going to lower excitation intensities, we finally find that we get for low excitation intensities a fast initial decay. So a lot faster than the recombination lifetime would suggest it to be. Looking again at the model, this could be understood if you only excite a small amount of charge carriers, a smaller amount than the density of vacant traps. All of them could be captured like very fast into the vacant traps and lead to a fast initial decay. And then again, for later times, to a re-emission. So this baseline here, it's not the background noise. This is again photoluminescence emission. Now, in the next point, I wanted to exclude injection density effects and also surface effects. Well, it could be possible that this fast decay is due to some injection dependence of the surface. So now I looked again at this dark blue curve up here, which was measured with a pulse distance of 2 milliseconds, so 1.5, 2 milliseconds. Now I repeated this measurement, but keeping everything the same, so pulse intensity especially, but I varied the pulse distance. So with pulse distance, now I mean here, you can see we have a pulse, we have the decay. Then after, for example, here 20 milliseconds, that was the blue curve, 20 milliseconds, we get in the next pulse and then the next decay. What we can do now is to make measurements with shorter pulse distances. Just this shouldn't change the electronic state of the conduction band in the beginning. But here you can see already, okay, here there's the next laser pulse, the decay, the next laser pulse. But even for the slowest pulse distance, we have the decay of the charge carrier density of 2 orders of magnitude, and here even more. So we can assume that at the end of the laser pulse, the conduction band is empty, and when the laser pulse takes place, the conduction band is exactly in the same electronic condition for all pulse distances. Now going to longer pulse distances, here we have 0 to 100 milliseconds, here 2 milliseconds for the slowest curve. We see again a fast initial decay compared to this exponential decay for the slower pulse distances. This again can be understood if we do not assume a rather small density, but we need just simply a higher density of traps, which is for the blue curve here with the 20 milliseconds. At the end of the pulse, most of them could simply all still be occupied. Such that if we now generate a lot of electrons, again only a small fraction is captured in the beginning. But now if we have a long pulse distance of 2 seconds, all of this large amount of traps could be emptied again, and then leading even for a high pulse energy to a fast capture of all electrons into traps. But what does it mean? This also means that here we can directly observe the capture. So I made a combined fit of the recombination lifetime. Here is exponential decay, which we usually expect to happen. And then the difference here between the initial electron density and the recombination electron density should just exactly be the amount of electrons being captured by traps. So we can put this into a graph, the amount of electrons captured as a function of pulse distance. And we can see that for longer pulse distances, more electrons are captured. If we now assume a thermal depletion of the trap levels, which would be an exponential depletion, we can fit here this exponential depletion, but we find that this doesn't quite well describe the situation. We would need at least 2 trap levels with different capture and emission time constants to describe this curve. Well, this is quite interesting because actually this was proposed 70 years ago by Hornbeck and Heinz that there should be 2 trap levels in their measurements. Well, this is interesting. There could be some quantities obtained like the vacant trap level density and depletion time constants. But I want to look a little bit more into detail with this decay. So I measured a lifetime curve over a very long period. So here with a double logarithmic plotting from a microsecond up to a second. And with one laser pulse in the beginning. Now this is composed of 3 different measurements with different time discretizations to obtain a low noise. And what you can find, we have different regimes. In the beginning, we have this exponential decay. So in logarithmic scale, an exponential decay looks like has such a shape. But these decays here, the slower ones, the emission of the trap levels, they do not look like an exponential decay. They rather look like a power law. So linear in double logarithmic scale. But actually, I do not think that this is the case, because if there's 2 trap levels, they should somehow behave the same physically. So there's no reason to assume that there could be a different power law dependence. And power law dependencies in general are a rather dangerous approach. Well, there's a few mechanisms in nature which are seriously power law. So I looked a bit more into detail, and I found the multiple trapping mechanism which was proposed by Hornbeck, which says that opposite to what I said before, that an electron is not captured once and then thermally emitted later back to the conduction band, but captured, emitted, recaptured, re-emitted, and recaptured, and this for a lot of cycles. So every time an electron is emitted from a trap level back to the conduction band, the recapturing by this or another trap level is much more probable than the recombination of this electron with a valence band hole. And then what does this imply for the decay characteristics? So this can be deduced from equations of continuity. So we have 2 equations of continuity. On the one hand, we have the equations of the electrons in the conduction band. On the other hand, we have an equation for the occupation of the trap levels. And if we solve these equations, this is possible with some approximations, we get a time characteristics which looks like that. So here T and R are reduced variables. So here T, we have here the trapping time constant, we have here recombination, the band recombination time constant, the average time of emission from a trap level, also here. So the time dependence of the charge carrier density is not exponential, but has a second term here in the denominator, which should vanish for long time decays, but before it's not exponential. We can fit this. So assuming these 2 trap levels are independent, we can first make a fit to the slow trap levels, and then add the fast trap levels. And actually, with such an approach, we can quite nicely describe this quite complicated decay characteristics. And I think here it's getting now interesting to do more measurements. So this measurement is just, I think, 2 weeks old, because if you see here that the fit should, for long decay curves, behave exponentially, but this is not within the measured curve. But yet I think that this is a quite new approach for investigating traps. Also because this fast capture of electrons or charge carriers at the beginning after laser pulse, this was the first time observed, and so we get a lot of information we can be drawn from here. So summing up, in the first part I showed you how transient photoluminescence spectroscopy can be used to obtain high time resolution and sensitivity, but also I told you that it's important to keep in mind that the evaluation and interpretation of data is not simple. Especially in silicon with a high diffusion length, one has to take care of that the experimental conditions are very well defined, and what is so that we have either homogeneous conditions in the sample, or we have to closely look into what is happening dynamically. In the second part I showed you how quantitative microphotoluminescence mapping can be quantified with such an approach, and how this technique, which is very sensitive in the time domain, can be used to separate surface and bulk recombination. And finally, a photoluminescence-based analysis of trap levels. So there will be more done in the future, and probably also in collaboration with UNSW, with our new collaboration project. This is why I'm here. So we have this new project, CCPV, together with ANU and UNSW, where we're very happy that we can now regularly come here over the next 2 years, maybe the next 5 years, to do research visits at your institutes, and that we can do joint workshops, a seminar like this here, experiments, and joint publications. So thanks all for your attention, and I'm happy for any question.
Thank you, Freddie. That was great. Any question? Yeah,
thanks for the great talk. It was really interesting. I wonder if have you attempted yet to try and determine trap energy levels and capture cross sections?
Yeah, I tried already 2 times and determined them, and after every time I just saw, okay, this wasn't fine enough. The mechanism is quite different. So the first approaches led to level trap depth of the one was quite central in the band gap. I think 0.48 electron volts, the other 0.7 distance from the conduction band. Yeah, but that was when I didn't look at this multiple trapping mechanism, so this could change some things.
So do you think it's foreseeable that it could be a really sensitive technique for low impurity concentrations?
Well, for recombination active traps, this is getting different, because then we do not see the capture and the re-emission, because we simply have recombination. So for recombination active traps, other approaches need to be done. So this is actually only for these special traps which have rather less recombination but high recombination and re-emission. But this will also depend on if this is actually an electron capture or if it has something to do with doping density. So this has to be clarified. So up to now, everything points toward an electron capture, because every other mechanism would need to be a lot more complicated, but still it cannot be excluded.
Yeah, thanks for the great talk. So can you say a bit about what you think, or how much you think all this trapping will or won't affect measurements that are closer to steady state? And all these sort of dynamic calibration procedures that we have developed and you guys have developed, and how this will all be affected by trapping. Have you looked into that at all?
Yeah, I think that depends a lot on the conditions. So for example, for modulated measurements, how fast the modulations are. It could be that these traps then only lead to a background noise, which is subtracted again. But especially if there's rectangular illumination, it could be rather a problem. Yeah.
Would be good to analyze that or quantify it, right?
Yes. I remember we talked already about this a year ago. Yeah.
Well, now's the time to do it, I guess.
Yeah.
Other questions?
Yeah, I've got one more. Have you looked at all this trapping behavior? Because you can, of course, obviously do mapping. Have you looked at sort of trapping maps in multi-samples, for example? Or?
Not yet. So these measurements were all conducted on a square centimeter diameter illumination, just to be really sure that there's no artifact. So I already saw, so as soon as, especially because all these dynamics are so slow, so when illuminating at a small spot, then this very defined 3 different regimes, they merge into each other and it gets to one blurred curve, because just traps successively fill by diffusion, and this is then getting complicated.
Other questions? Anything from people? Okay, let's as I say, Freddie will be here next week, so if you have other question or thought something, just approach him. He will be in level 3, but also in LG25. Let's thank Freddie again for great talk.
Thank you.